Good afternoon, my name is John Ellis, and I'm president of Si2, Silicon Integration Initiative. And this afternoon's panel discussion will be on challenges and opportunities in global standardization of compact models. We're really fortunate this week that the Compact Model Coalition is having their face-to-face meetings the next 2 days at NXP here in Austin. And so some of our illustrious members have joined us today for a panel discussion here at DAC. So a little bit of background on Si2. Si2 is a research and development joint venture. A research and development joint venture is uniquely different from a standards development organization in that the members themselves are protected in working together collaboratively on projects. A standards development organization is unique in that the standards development organization itself is protected, where the members are not. And so what we do at Si2 is we do projects, proof of concepts, design, kind of interoperability, adoption tools that lead to standards and the adoption of standards. So what we've been doing even this past year with this shift in emphasis, and I say shift in emphasis because over the past, 10 years or so, it's really thought that we were a standards development organization, which put us more in competition with standards development organization groups. As such now, we'll be making donation, for example, in Low Power Coalition, of some of the work that we're doing into IEEE for final standardization. So the thought is, we can do proof of concepts. We can do collaborative type of efforts to test things before they become standards, to accelerate the adoption of the standards. And so our primary initiatives, most of the industry has heard of open access. You may not have used it directly, but the tools you use it. And most leading edge companies, they'll develop scripts and their own tools to get access to the database, but this is a leading IC database for design tool interoperability. The other major initiative we have is Compact Model Coalition. Now, Compact Model Coalition was its own entity for many years, and they came into Si2 just a few years ago, and I wish all of our groups were as active as CMC. The leadership here doesn't compare, I mean, it's above and beyond anything we have in any other group, and that's not to say anything bad about the other groups, but it's just so impressive what this group has done and the leadership they take and the ownership of the group. They really do own this. And so the positions of chair, vice chair, secretary, and treasurer are not just titles. These guys really do the work. And so what Compact Model Coalition does, they do SPICE simulation models that are incorporated into the IC design tools. And finally, Open Standards is a collection of a number of different projects that we have. Chip package co-design, low power. We also design for manufacturing, Open PDK, and silicon photonics. And so that's one comprehensive program that there's one fee to join all the projects. What's unique about this as well is that we now have a new structure so we can quickly start any other project. If someone has an idea in this area, all they do is write a proposal to the board of directors who can quickly, within a month, start a new project as long as it meets their criteria for what a new project needs to take on. This is really project-focused, project-based, not just an ongoing coalition like some of our other groups. It has to be focused with a beginning, a deliverable, and an end. And so, Si2 membership, we include the EDA supply chain, which means the EDA companies, fabless, and foundries, and integrated device manufacturers. So on this next slide, we have a list of really all the logos of the members we have. There should be about almost 70 members up here. And you should be able to find your company up here. Within CMC, we have 31 members. And so what we're going to do now, I'm going to introduce the panelists all at once, and then we'll ask you to come up one by one and give your presentation. And then we're going to save questions for the end. And so I'm not getting on my iPad here to browse the web. I have the descriptions here. So going from right to left, our first speaker will be Dr. Peter Lee, who's a manager at Micron. He's presently the chairman of the Si2 Compact Model Coalition and a senior member of the IEEE. Dr. Lee has taken this position just this year and already having a great impact, previously serving as vice chair. Next to him is Dr. Rob Jones, senior principal engineer at Raytheon. He's focused on device modeling and foundry services at Raytheon in the microelectronics engineering and technology department. Next is Marek Mrzwinski, excellent, software development engineer at Keysight Technologies. He's responsible for the compact model devices and Keysight's Golden Gate and Advanced Design System simulators. Next, we have Dr. Joseph Watts. He's principal member of technical staff at Global Foundries, but he was with IBM for 35 years and was part of this transition over to Global Foundries. He's presently vice chair of CMC, but he's also served previously as secretary at CMC and chair of CMC for many years. So lots of experience and background here. Richard Williams, who's heavily involved in a lot of different working groups. And so Richard is an IBM senior engineer. Just so you know, a senior engineer is a very high position at IBM. And he works in the IBM Product Technology Engineering Group in Burlington, Vermont. He has 65 issued patents and many awards. He's secretary for CMC, and he chairs the Multi-Gate Models Working Group, which has CMG, IMG. And so, so first up, we're going to have Peter. I'm going to get your presentation up here.
All right, thank you, John. My name is Peter Lee. I'm presently the chairman of the CMC, just started this year. Thank you very much for joining the panel discussion. We joined the Si2 about 3 years ago. However, the CMC itself, this is actually our 20th anniversary. So we've been there for 20 years, since 1995 is when it was first created. So just, I'm going to give a little introduction of the CMC, why we have the CMC, for instance, and then the other panelists here will discuss more of the details of why we should have the CMC, how they've take advantage of it. Previously, before the CMC, we have a lot of different compact models for different devices. Used to be maybe a lot of IDMs, companies which had all the process, design, everything in one. And they were also developing their own internal tools, and some of these would be developing their own models. So there wasn't much issue there, but now, since the 1990s, we've had the model where we have a foundry, and we have a designer, which is in the fabless company, and then you have EDA vendors in between with circuit simulation, where we have these models in place. So we have these standard, or what we so-called standard models that are typically developed by research institutions. However, they may be implemented in a certain vendor tool, circuit simulation tool, in one way. A different vendor may have the same model, but may not be completely compatible. There's no way to ensure that you're going to get the exact same behavior. And then you have maybe another vendor, and you have these different fabless designers, which they will choose different vendors depending on their needs.
And they'll have inconsistent results because the models themselves have not been standardized. So you could have the same Model 1, but then result in different implementations, which show then inconsistent results. Which is what this is, yeah. So to solve these inconsistencies, which result from using these different implementations of the same model, but with different vendor tools. So a group of foundries, fabless design houses, even IDMs, EDA vendors, and universities got together in 1995 to form what we called back then the Compact Model Council, or the CMC. So the major goals were to create a standardization body to solve that model inconsistency issue, and also create a system to fund the model developers so that these models would always be up to date and serve the needs of the industry. So most of these models, at the research institute level, they put in the physics and try to fit the physical characteristics, but then you always need to get that feedback from the industry on what their priorities are, what kind of mechanisms they need. So that is, and the CMC is a way to then feed that back, plus give the funding to do that development, to industrialize the model. So thus CMC was born in Washington, D.C. on December 15th, 1995, which is 20 years ago. And as John mentioned, right now we have 31 member companies, we list here, which represents pretty much all over the globe, from the United States to Europe and Asia. And they represent the full spectrum from design houses, IDMs, vendors, foundries, etc. This is just a brief history of the models that we've standardized in the CMC in the past 20 years. Starting out with the BSIM MOSFET models. That was the first one back in 1995. But since then, we've had all these different models and all these different device types, first starting out from planar bulk MOSFETs, going to LD MOS, SOI MOSFETs, bipolar, and now going through like multi-gates. And then also some other non-MOSFET type, non-transistor type things like MOSFET actors, resistors, junction diodes. And we're also standardizing things that are not really, they're not models themselves, but are related to them in a direct way in terms of like API and standardized SPICE language. And also one big shift that we've done starting off from after BSIM 4 is we are standardizing now on using the Verilog A code, which makes it much easier for the model developers to concentrate on developing the model and not to debug like C code or C++ code. And then, as John mentioned also, we have a lot of different working groups which are specifically concentrate on each of those standards, making sure that the industrial needs are met by these models and making sure that the funding goes to those model developers. So we have the whole set of models here listed, and we have a working group chair for each of these models that leads those working groups. And we have discussions at quarterly face-to-face meetings. And currently we have 17 working groups. And we have recently the new standards that we came out with last year had to do with ultra-thin body SOI, called fully depleted SOI. So we standardized both BSIM IMG from Berkeley and HISIM SOTB from Hiroshima University in Japan. And we'll also standardize a accurate forward and reverse recovery modeling in the diode CMC model. And then the key initiative now since we started last year and going on to this year is in the gallium nitride HEMT area. This is the first time we've gone to this type of device for power and RF. So we'll be going into that, hopefully standardizing a model this year. So what the member benefits have, if you become a member of the CMC, members have a say on what models become a standard. So they have exact balloting rights. When we do a new standardization effort, we have candidate models from different organizations. So you have a right to vote on which ones you would like to have as standard. For models that are already standards, you have the opportunity to request enhancements. What enhancements have the highest priority, for instance, that will meet your needs? Members attend quarterly CMC meetings with leading industry and academic developers. They learn about the technology often before they're published in literature, so before they're open to the public. Members have access to model beta code so they can test and then feed that back to model developers. And then also have access to functional assets such as model implementation QA suite and some of the API code. And a lot of this information is only available to members only on the CMC website, which is on the Si2 site. And this is just a summary of some of the model developers that we are involved with now that do the actual model development from Berkeley, Hiroshima University in Hiroshima, Japan, UC San Diego for bipolar HICM, Auburn University for MEXTRAM, and CEA Leti for the PSP MOSFET model standard. And as a summary, CMC enhances the IC development process because we standardize all these high-quality models and simulator interfaces. And then we also provide this technical forum and mechanism to keep these standards current and meeting industrial needs for the expanding use. And CMC is a member-driven organization, and it's open to anybody in the semiconductor business. And you can find more information at this link at the Si2 website. I think that's it. Thank you.
And we'll save questions till the end. So, Rob?
Good afternoon. I'm Rob Jones. I work at Raytheon in Massachusetts. We've been a CMC member now for a few years, and we joined specifically because of the GaN HEMT standardization activity that Peter mentioned. And I'm going to talk a little bit about that, and I'm also going to hopefully give you a little insight into why Raytheon cares about standard compact models and what got us involved. As Peter said, we've started working on a standardization effort for a GaN HEMT model for RF and power applications. We basically have a 4-phase process that we go through to standardize models. Call for models, developers do a self-evaluation, then member companies evaluate the model, and once a standard is chosen, we prepare that for general industry use. So we're right now in the 3rd phase of that process where CMC member companies are evaluating a few models. And I have a little more detail in the next slide. We come up with some technical requirements typically for the model. In this case, we were looking for a physics-based model, preferably one that was surface potential based. We want to make sure that it behaves well, so it meets the Gummel symmetry test. And we have some requirements on how well it's going to be supported, what kind of documentation is available, what kind of organization is available to support it, what the maintenance plan is. For both RF and power switching applications, we're looking at a device, a HEMT device that looks like this, with one or two field plate structures, gate connected and source connected field plates, for example. The access regions in these types of devices are often behave in a nonlinear fashion, so those are treated either as a transistor or as a nonlinear resistor. So all of these things are things that we're looking at for the model. The current status of this activity is on this slide. So back in 2013, there was enough interest within the CMC to see what standards or what GaN HEMT models are out there in industry or in research, in academics, that we could look at standardizing. So a call was put out for models back in 2013. There were 8 candidates that were identified, and that's kind of phase 1, figure out what's out there. The eight of those candidates presented at our Q4 meeting in 2013. 4 of those models found sponsors within the CMC, so they went on to phase 2. And they're listed here, MIT, UNIC, and it's involved a couple of the universities now, Leti, and the Angelov/Chalmers model. Those are the models that were looked at in phase 2. And in phase 3, we down selected to 2 models, the MIT and UNIC/Berkeley/IIT model. And presently we're in phase 3 where member companies, including Raytheon, Analog Devices, TI, Infineon, and Toshiba, are evaluating these 2 models. Doing things like extracting models for these companies' different processes, evaluating the performance against measured results, and really looking at FET and circuit level performance and convergence properties to make sure the model is, the final model is well behaved. So I'm going to talk a little bit in the next 2 slides about Raytheon and why we're involved. So you might, if you've heard of Raytheon, you probably think of us as probably a big system integration company. What you probably don't know is we have a state-of-the-art gallium arsenide and gallium nitride fab in Massachusetts, in Andover, where I work. It was opened in 1984. It's a DoD-accredited trusted foundry for the government. And we have semiconductor fab, we have MMIC design and test, we have modeling. We develop modules and develop prototypes that end up going into our systems. So I'm involved in the modeling side of things, and as you can imagine, thinking about us as a big system integration company, we have pretty lean fab and a support group, so my modeling group is very small. And that's one of the reasons why I wanted to get involved with the CMC. So augmenting the staff I have was a big draw for me. So we have a small team that's basically supporting the process we have in developing models. We don't have a lot of people available to develop new models and add new features to models. And that's where the CMC provides a lot of value to us. We don't have to do all the work to develop the model and maintain the code. We can really focus on developing the best characterization techniques and the best models for our processes. It allowed us to really accelerate physics-based compact models for our devices. If you know anything about the compound semiconductor world, most of the models that are available are very empirical. There really have never been standards in that area like it's been developed over the last 20 years in silicon technology, CMOS, et cetera. So this was another big draw, and that really allows us to provide robust and physically based statistical models. And the models in some sense give us a predictive capability, at least for layout changes, but potentially for some material changes in the HEMT stack up. And lastly, we have amplifier designs, switch designs, and some multifunction type chips. And we use a range of FETs, from amplifiers to switch FETs, and FETs with a range of gate lengths in some of the multifunction applications. And so historically, companies like us have specific models for switches or for amplifiers or for each discrete gate length. And the kind of model that we're looking at here for GaN HEMTs allows us to have a single model that can support all those different types of devices. So a lot of benefit to us, and we hope that you see that value as well, and will consider joining the CMC to help us with this activity. So, thank you.
Thanks for that nice plug. And so next, Merrick?
Hi. Yeah, I'm Mark Mrzwinski. I'm with Keysight Technologies, which formerly was Agilent Technologies, which formerly was Hewlett-Packard. And we're an EDA vendor. We developed some design tools in order to develop a lot of the high-frequency equipment and instruments that Hewlett-Packard, Agilent, and Keysight made. And we've been very interested in the CMC from the beginning, because our simulator was a high-frequency simulator, and over time, a lot of our customers wanted to start using our simulator with their lower frequency tools and wanted to share net lists and models and things. And there was an awful lot of trouble with very simple things keeping models from working together. And we'd spend quite a bit of time trying to get the models to work properly in our simulators, because being a high frequency simulator, it used a different kind of solving and harmonic balance rather than time domain. So standard models for us really reduced the complexity of getting working models into what we really wanted, which was our product chain, and ultimately to the model developers and circuit designers who really needed to use these models to get their circuits out. And the past where users wanted to be able to make individual customizations to the models was pretty hard to do, but with the standardization process, and especially on standardizing to Verilog A, users can now use standard models and also make their own customizations when they really, really need to. So for our tool set, which covers both simulators, Advanced Design System, Golden Gate, but also the model extraction tools like ICCAP and the model builder and QA programs that we have, it was a lot of work to try and keep track of all the different versions that were coming out by the model developers, as well as the changes that individual EDA vendors were making. So having the Compact Model Coalition standardize on these things, it both helps the EDA vendors and the end users ultimately. And the reason is, I mean, compact models used to be a competitive advantage. We made our own compact models, and we still do. But really, the ecosystem for getting all these parameters extracted, getting these design kits implemented, and getting support for multiple simulators is a huge commitment of resources, and you can't do that just because the model is a little bit better. So customized or proprietary compact device models really do have a competitive advantage anymore. It's a very rare case that happens. And foundries, they really just want to get as many users to use their tools so that they can get their foundries up to full capacity. So they want to support all the different simulation tools that are out there. And really, the compact models have gotten so complicated. It's not that easy for users to investigate, implement their own flows to extract models for every single model that's published, just because it sounds like it might do a better job. And as I mentioned, these models have to work in time and frequency domain simulators now, and that is kind of behind the scenes things, but getting that to work right is a lot of work as well. So the advantage to the Compact Model Coalition to us, an EDA vendor, is we end up with a very predictable roadmap. We know when models are coming out that are going to be popular with the end users. So they tell us when they plan to get, and we see them working on it themselves, so we know that they're going to need a model at a certain times. But the release procedures are consistent, so we can plan on when the model is going to come out from the developer, when it's going to get QA'd, when a final release is going to be available. And having a lot of different users in the Compact Model Coalition check it out, they check for correct behavior, so we find a lot of the bugs ahead of time rather than after the model goes out and iterating through multiple simulation releases. The CMC gives you QA suites. They always can be compared against the Verilog A reference, so it's simulator independent. And as I mentioned, the crowds testing all the models means bugs are found faster. And versioning, just being able to say what version of model, even though that sounds like an incredibly simple thing, is very important. So you know that you're getting the exact model between different versions of simulators and vendors. So thank you.
When John invited us all to talk, he said, 1 or 2 slides, 5 minutes. So apparently I'm the only one who can count to 2. So as John said, I'm with Global Foundries. It's pretty obvious that Global Foundries is a foundry. You may not think of IBM as a foundry. That's not their primary business. But prior to coming to Global Foundries, I was involved in IBM's foundry business. And we've actually been in that business they were in that business a long time until they became part of Global Foundries. So back before there was a CMC, when we were first starting to try and get into the business as a CMOS foundry, there was what you could really call an industry standard. It was a de facto standard, level 28. It was a proprietary model from a particular EDA vendor. It was actually, at the time, a very good model, but it was proprietary. If you wanted to fit your technology to it, you treated it as a black box. They would not tell you what the equations were. So fitting as a black box is possible. We did it, but it's not a very good solution. And if you had a customer who didn't want to use that tool from that vendor, you had to do something else for them. We actually also experimented with delivering our own model. We had a proprietary in-house model because we were an EDA. We had our own technology, our own models. We had our own simulator. We had our own EDA tools. We tried to port that model into that same vendor's tool as level 48. And I don't really remember exactly how that all worked, but I do distinctly remember spending all of a 3-day weekend debugging a problem that turned out to be an underflow of an exponential that only happened in one particular operating system. It was very ugly, and so that was not an ideal solution for us. So that was the motivation for us to get involved with the CMC, that there would be a standard model. We would not be responsible for making the model run in every simulator and on every operating system. And we weren't even responsible for developing all the physics that went into the model. We were just responsible for making the model fit our technology, providing that to our customers. So there's a lot of EDA vendors out there. If you try and provide your own model, and you can do that. Merrick mentioned the Verilog A. You can make your own model, stick it in Verilog A, and virtually everybody can run it. But it runs really slow. And it's not quite perfectly true that everybody's Verilog A compiler always gives you the same result. So the QA that goes into the CMC models is a big benefit in terms of actually getting the same result in every simulator. And the EDA vendors tend to give priority to CMC models because there's a lot of users for CMC models. EDA vendors, like everybody else, responds to their customers. If you got a lot of customers that want that model, you're going to make sure that it's in there. You're going to make sure that it runs correctly. You're going to make sure that it runs efficiently, et cetera. Now, as a foundry, one of the things that we try and do is provide differentiation in our technology. And in some cases, that means that a transistor which has some additional features, or a transistor where we have pushed the technology to where it has an additional bug or a bump or a strange behavior that you got to model. So how do you get that into a standard model? And that is a process that the CMC provides. Basically, it works like this. You look at your data and you see this thing and you convince yourself that it's real in the data and that you've got to model it. So then you take your data and you disguise it so you don't give away anything about your process, and you take it to the CMC and you share it with all these guys and say, look, this happens in our technology. It isn't included in the model. We've got to update the model to fix it. And probably some of them are sitting there saying, yeah, I saw that in my data too. I don't know what it is, but we got to model it. So you agree, we're going to model this. You give it to the developer, which is usually a university. We have non-disclosure agreements with all the universities we work with so that we can give them the real data, and it's protected, and they can make the changes to the model, make sure it fits our real data. It comes back to the CMC, it gets reviewed by everybody, it gets tested by everybody, and eventually it gets released. One of the reasons that I'm a chairman of a working group is there's a model that's really important to us, and I want to make sure those releases happen on our schedule as we need them. But, we support everyone. Okay, other people are doing the same thing. So I don't have to discover everything and figure everything out. Other people are going to be finding those things, and it'll be there in the model when it shows up in my technology in many cases. And finally, the quality piece. If I make a model and I test the model, I'll find some bugs and I'll fix them. If I've got 5 different companies who are going to either implement that model or use that model with their technology, they're all going to test it. They're going to find those bugs faster. The model quality goes up much more quickly. So that's my one page. Thank you.
Good afternoon. I'm Richard Williams with IBM. And what I'm going to do is give you the perspective of a fabless user, and I'm also going to be giving you the IBM perspective, which Joe has just given you some information, some background on. And I think what I'd like to also do is reinforce some of the procedures that we do to create a model standard too. As a chairperson of the multi-gate models subcommittee, we had this is the except for the bulk BSIM-3, BSIM-4 subcommittee. I think our subcommittee has produced the largest number of CMC standard models, and these are all variations on different types of MOSFET architectures. So one of the things I wanted to emphasize is that our view as IBM as a fabless company is also the same view, as Joe mentioned, for a foundry. In fact, we're a captive foundry, which means we do everything from soup to nuts to create our own in-house technology, the PDKs that go with it, the circuit design that uses the PDKs, and then the final products. And so the main revenue driver for us was making high-performance, really large servers for the government and banks and industry, which needed to build things which ran really fast and could crunch a lot of data. So these are sort of an alternate view of thinking. If you look at many of the displays that are in this auditorium, a lot of these people want to do high power, so they can put a little chip inside your tennis shoe. That's not actually the market that we're going for here. As a fabless company, now things are a little different. So as several have mentioned, we sold our microelectronics division effectively at the end of June last year. We still have the need for PDKs. We still make high performance microprocessors and server products. And so but we rely on a foundry to provide that. And Global Foundries right now is the foundry which provides those chips to us. But it's an adjustment for us, and we have a group of which I'm part of, which works with PDKs provided by foundries, and we sometimes there are some things which we need to add to the PDK for our purposes, but that's generally the very rare case. Usually, with everything has to come in the PDK. So that sounds like a big change, but does that really affect everything, such as the compact models? And I'll say not really so much. And I guess I'd like to expand on that a little bit too. So one of the things that we were doing originally, before the breakup, we had a lot of very specialized things. And again, it's the idea where if you're developing your own models and you're supporting your own models, and you can throw a lot of people at it, you can do a lot of things. The problem is that does take time, that does take a lot of people, a lot of focus. And if you're working in an environment which has to work with lots of different pieces, lots of different EDA tools, including circuit simulators, then you've got to make sure all that works together. And so it's a big effort, but for working for someplace like the CMC, for a relatively small amount of money, a relatively small fraction of a person's salary, you get all the benefits of the CMC, which are high quality models. They're delivered on a fixed schedule. They have the features that you want, plus features that other people may have seen that are also relevant and physically real. And it works across all simulators. One thing that you should be aware of is that to be implemented as a CMC standard in other simulators, what the CMC does is it goes through a so-called QA suite verification process. So that means that the model developers run a certain set of test net lists, which are generated by a program which covers a wide range of test cases, and that produces a bunch of reference results. And then all the vendors that support the model have to go and reproduce that same set of answers. And so right now we're at 6 or 7, depending on how you count it, EDA vendors. And so that's a really good, for us, that's a really good standard of goodness to say that all those companies match that same data. So that means the implementation and the model are working as expected. So fabless. So for us, right now it's actually a bigger deal, a much bigger deal, that things like the CMC are working properly, and that's one of the reasons why we're still a member of the CMC, because we need to make sure that that model is exactly the right thing. We do a small amount of customization once we get a PDK, but we still need to make sure the underlying compact models are doing the right thing. So again, it's really the same value statement that I mentioned on the previous slide. We want to make sure that it's high quality, relevant, and it's consistently implemented across different simulators, because we do have different types of simulations, and we do need to make sure that same model works the same way in all those simulators. So I guess in conclusion, that for the CMC, it's now more than ever, it's important to have CMC standard models, and for groups like IBM to participate in the CMC. Thank you.
Okay, now we're ready for some questions. And so, you know, some of the questions I distributed to the members that I was going to ask, you guys already answered, such as what were the big benefits. If there's any specific, we'll need to turn the mics up for all of them. And you have to share mics too. We have 4. But if there's any specific instances, especially with some of you with your long history with CMC, where CMC and your participation specifically solved a problem that just you wouldn't have been able to solve easily otherwise. Joe, it seems like you got one.
So, last year we had a customer.
Actually, speak up, get up to the mic, and it'll be better.
Speak louder?
Yeah.
Okay. All right. So we had a customer last year who wanted to connect an external thermal node to their the thermal node of a high voltage transistor so that they could model flow across the chip. And you could argue whether it was a bug in the model or the model developers just never anticipated that you would do this. But when you connected it and you tried to do that, you got very non-physical results. Now, if we were delivering our own model, we could have fixed that, and we could have then gone and worked with all the vendors to try and get that implemented. Or we could have worked with only the vendor that customer was using, although they were using 2 different EDA vendors and they needed it in both of those 2 tools. But by working through the CMC, we were able to show the data, show the simulations at the CMC, work with the model vendor, which in this case was Hiroshima University. They made the changes. We had a bunch of phone meetings so that we could get everyone in the CMC to agree quickly and roll a release out in a matter of weeks. The vendors then rolled it out into their tools, and by working with the CMC, we still had the same model in all the EDA tools for this customer and all our other customers.
Excellent. Anyone else? Yeah, Peter. Okay.
And just as a general comment, whenever you do have needs that you want to have a model improved, it is a lot easier now to motivate the model developers to implement those needs, because you'll have the backing of the CMC. It's not going to be like a customized model just for that company, for instance, which may not be used by any other member. So you get the full endorsement of the CMC. You get that publicity also that you got that in the model. So it's it's much easier to work with the model developers to get it implemented.
You know, one instance I saw at our face-to-face meetings, and this is one of the benefits we have, is, and I know they're sometimes tough to get to, but the face-to-face meetings are a big benefit. There was one time at lunch, I was sitting at a table with a number of technologists and Dr. Chen-Min Hu, and someone raised a question that they'd been struggling with, I think it was on BSIM CMG, for weeks, and literally in about 2 minutes, he straightened them out, solved the problem so quickly. You know, it's the face-to-face contacts with the developers who did the research on developing these models is really priceless. So certainly one of the benefits. So another question I have, because I wasn't around when you all decided to start working on the gallium nitride model, but there are other models coming up. For example, silicon photonics. At some point, you know, there seems to be a big interest from our membership on when we're going to start developing standard models. Whoever has experience would like to describe how did the gallium nitride, you know, model even get started? What happened there, and what might happen for silicon photonics if and when that's ready? Rob, get up to the mic. There.
I was not a member of the CMC at the time it started, but I believe that there were several member companies that expressed interest, probably more for power management, for power type devices. But when I saw that was happening, I got Raytheon involved, and you know we're still trying to recruit other RF companies. There are a few other ones that are involved. Infineon, for example, is looking at the GaN model for RF applications. But really it comes from member companies and what they want to see available as a standard model.
the CMC actually has a standard regular process for considering what new models or what new projects do we need to look at. So at the, I guess we're going to move it to the December meeting, but it has been the January meeting where any member can come forward and say, we should go work on this, whatever this is, tunnel FETs or whatever you think we ought to be working on. And then you have between then and the next meeting to recruit some other people who want to work with you. We have a criteria that says there has to be someone who's willing to actually chair the working group, and there need to be 3 other member companies in addition to the chair who are willing to work with them, so that you don't get a lot of groups that are not doing anything. You only create groups that people are actually interested in working on. And then you have to get the support of at least half of the other members to vote and say, yes, I think that's a worthwhile thing to do. And if you meet those criteria, then the working group can begin to go off and do whatever it is they think needs to be done.
Yeah, Richard?
Yes. I have one other aspect of this which hasn't been mentioned, but it's a very important piece, and that is one of the things that the CMC does collect dues, and it's not a small amount of money, but it serves a very important function, and that is we do fund the model developers, the 6 names that we showed you up there, to productize, to make it into a production level model, and to maintain it. So I think this is it helps keep the synergy going, so to speak, and it certainly helps keeping the models going too.
Yeah, back to the gallium nitride aspect of that. I mean, from an EDA vendor, what we saw is users taking the existing gas models in Verilog A and modifying them, and then using them as best they could, and working with the model developer, who then was generating multiple versions, which then customers were asking us about when we have some history of it, but some we didn't know what was the differences. And so at that point, I think that was enough to come back to the CMC and start saying, there's enough interest from customers, let's start looking at standardizing.
So at the same time, you expect to see a lightening of your workload and
definitely,
supporting all those variations.
Assuming that we go from the 4 original down to 1, not
right.
4 down to 5 or something.
That would be the wrong direction. So we're going to take some questions from the audience. We have time for a few questions, and I'm going to disconnect the mic here because I want you to use the microphone if there are questions. So are there some questions from any audience members for our panelists? These are the world-renowned experts in this. There's your chance. Otherwise, you got to pay to go to the face-to-face meetings, I'm telling you. If not, we're going to go ahead and draw it to a close unless you guys want to ask each other a question here in public, kind of corner somebody. No? Great. Well, thank you very much, and if we could give them a round of applause. Thanks.